Okay, so this dl by L is actually negative, right? Because we still have the negative from here. All right, so going back to this equation, it's going to be negative here. So the diameter as a function of x is basically 2 times d minus dx by L. Okay, so factoring out a d, that's our equation for that first piece. All right, and then the diameter of the second piece is constant, so we don't really need to worry about that so much. All right, now into the polar moment of inertia of a thin section. So we know that the definition of the polar moment of inertia is actually the integral of a distance squared dA. Okay, that's for a generic piece. Now, if the wall is thin enough, all right, we need to do a slightly different step in this integration here. So the dA, if we're using a radial coordinate system, all right, so dA is going to be r dr. All right, and now actually d theta as well. Okay, so plugging that back into here, j is the integral of r cubed dr d theta. Now, for a thin-walled piece, or let's just explain it slightly different. For a thick-walled piece, we just sum up the dr from 0 to some distance r, and that would give us the r to the 4 by 4, and then the 2 pi takes care of the rest. But for a thin-walled piece, we're going to say that the thickness can be approximated by this dr, right? Because if you imagine this, what this actually looks like, all right, this little dA here, it's this area here, all right? And this side length here is rdr, or rd theta, sorry. And this side length here is dr. All right, where like this goes back to like the center of the circle here. So we're going to say that this thickness is equal to dr. All right, for an approximately, approximate polar moment, assuming t is really, really small, which in our case it is. So t is constant, that comes outside. We're left off with j equals to 2 pi r cubed t. All right, so this is j for like a, a thin-walled section. I'll just call it t. Okay, so we need to find, once again, our j as a function of x. And we're using this thin-walled section. We use the thin-walled piece for this as well. So we can say that j for the, the angled section is 2 pi t. Now the radius as a function of x. We know the diameter is a function of x. So let's just get that happening. So it's going to be the diameter as a function of x by 2 cubed. Okay? So that's the situation we want, and we know the diameter. So let's just simplify this and plug in diameter as a function of x. So JA as a function of x is equal to pi t by 4, the diameter as a function of x, right here. Alright, so that complicated looking thing, that's what we got to plug into the bottom of our integral. And the j for the solid piece is just going to be, this right here. Instead of radius, we're going to put in diameter and factor this out like we did here with the 2, and it's going to be this, and then instead of this big thing, it's just going to be d to the 3. Alright, so this is all the ingredients that we need. So it's just a matter of plugging it in and integrating. So I'm going to work out the integration on the next page. It's rather long and tedious, but that's alright. So the first step then is to plug in all the values. So the phi total then is the integral Okay, so this is the fully expanded form. So for each of the individual values of t, let me just pull back this equation here. All right, so TA, that was t by 2. We plugged it in. G, JA, that we found before, we plugged it in. TS, that was t over GJ of that piece, which was pi by 4 d cubed t. All right, so now I'll just be quiet for a little while and just go through and integrate this thing. Okay, and that's the final answer for this first piece of elongation. So the total elongation then is this plus that. Okay, and that comes out to be 19. All right, the final elongation. Now, let's go ahead and plot this. All right, and here's where things get a little bit interesting. All right, something I haven't quite been able to figure out. We know that the wall is, the wall is like fixed and the bar is fixed to the wall. So when it's on the wall, there should be no rotation. All right, but when x equals 0 in this equation, then we're still going to have some sort of amount of elongation. All right, so it's basically like it starts somewhere. Okay, so we'll just, just take it at that. And then we solved this piece here is actually the, the displacement or the rotation of just this angled piece. And it goes up to about, here. It's going to be linked by some sort of curve like such. And the next piece, that's just going to be linear up to the point here. All right. So I'm not quite sure what's up with this initial bit of elongation, but for the purpose of this question, the whole thought process behind it is to go through the steps of finding all the individual pieces, going through and integrating it. I have to admit, it took me a few tries to get this integration right, so I could show you guys how to do it. But hopefully I was clear enough. Alright, thanks so much for watching, guys. I hope this video helped you out, and I'll see you in my next torsional bar video.